So first, I would like to thank the organizer for the very kind invitation. I'm pleased to be here for the first time. And I would like also to congratulate Professor Dani for his birthday and for his wonderful scientific achievements. And thirdly, I would like a bit to apologize because you will not see much dynamical systems, no ergodic theory in this talk, but I hope you could be interested anyway. So I will speak on rational approximation in P-adics. So I first recall that if you take some rational number alpha, so then there are infinitely many rational x over y such that x alpha minus x over y is less than 1 over square. And you have the corresponding result in P-adics. So you take P a prime number, psi into P or maybe ZP, I prefer. So irrational. And there exist infinitely many AB integers such that the P-adic value big psi minus A is less than maximum A B to the minus 2. So you have to adjust maybe with a P here, something like this. So here y is the maximum in absolute value of x and y. So alpha is real. So x and y are of comparable size. But this is not necessarily the case here. So there is no reason for A to be comparable to B. So B could be 1 and A could be very large. So and say that X should be comparable to Y, but A has no reason to be comparable to B. So actually, we have a result can formulate this result in this way. So you have I am in P-adic. So I will take psi a unit. So maybe it's better to assume this. Okay. And then B and A are not divisible by P. So if you divide by B, here this will remain unchanged. So BP will be 1. But if you want to excite the unit, you want psi minus something more. Yeah. Yeah. So A over B must be a P-adic unit. Yeah. 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 The P-adic norm. But it's not the P-adic norm. It's the absolute value of integers. Sorry. Yeah. Yeah. That's that's the usual absolute value with integers. Yeah. Yeah, well, it's Minkowski. It's just Minkowski statement, like here. But I prefer to say that this follows from continued fraction expansions. But that's P-adic Minkowski. You just have to adjust probably with this P. I haven't checked. It's the same things. You have your convex body in. Actually, you can see this multiplicatively. You have infinitely many. Well, this implies this statement. But, otherwise, you can put your convex body. If you want to see something like this. There is an integral point in this convex body. So when you write like this, so in the reals, there's no reason to do this because it's the same thing, because x is comparable to y, so there will be no change. But in the p-adics, this changes a lot. For instance, if you look at this statement here, there are some psi for which this is best possible. I mean, there are some psi for which we have this for some positive 6 psi for all AB. These are psi which are called badly approximable. And like in the real case, and we also know that they form a quite large set of full Hausdorff dimension. Zero R measure, but full Hausdorff dimension. Okay? So you can ask similarly this kind of question with the multiplicative point of view. State this a bit differently. Is it true that the infimum of AB big psi minus AP is always 0? So this is a little root type problem, actually, and this is open. And so I will discuss briefly some results towards this question in the first part of this talk. And in the second part, when you look at things like this, with the multiplicative point of view, you can define exponents of approximation. So like irrationality exponents in the case of real numbers. And this will be the second part of the talk. So the question, so first, I will discuss a bit this. So I think the very first, so it's clear that this is true for almost all psi. The only possible exceptions are the psi which have this property here, which are badly approximable. And the first result is proved by Einsiedler and Klenback, even if it's a bit hidden in their statement. So they prove that the set of exceptions, if any, as of the dimension 0. Recently, de Matham proved that we'll call this star, that star holds for psi quadratic. And even a bit more, you can add some logarithm of AB. Also, yeah.
Somehow I'm confused. I'm saying that the subscript B on the
Is
it just a different problem? You need to start with a real psi and study the real distance with the big psi minus A, and then multiply by the P-adic value.
Say it again.
I want to ask regarding the same problem that you mentioned here.
Yeah.
But I think of psi as real.
Yeah.
And I flip the P-adic norm is on the left and the infinity norm is on the left. Isn't this what the Klenback
There are two variables. And if I remember correctly, their paper, there were psi and psi naught. So one of the corollary of their result was
what I
said, and another one is this one. And the connection between both will be written here soon. But it's, so the problems are probably different. Now I can say two results obtained jointly with Dmitry Badziahin. So the first one is in this direction, but much weaker than a counterexample to this. So there is some positive delta such that the set of psi is the infimum of AB for the set of exception as full out of dimension but unfortunately we have to add something here and something which is a log times a double log. So that of course, if you want to, so the set of psi for which this infimum is 0 as full R measure. So this is not completely obvious. But I said that the set of psi for which this infimum is 0 is large, so as full measure. Almost all psi doesn't satisfy this. But that's in this sense, this is not trivial. Well, I don't know. It may be the best. Yeah. It may be best possible. I would be surprised, but I mean, yeah. I would be surprised. So now I can answer your question or your remark. The difference between the statement you put and the statement I wrote, it's also what we proved with Badziahin. So if the infimum for every over Q alpha QP, this is the distance to the nearest integer, 0, every alpha real, then the problem considered here, the infimum is also 0 for every tiny QP. So this is often referred to as the P-adic Littlewood. So we know that the set of exception, if any, has Hausdorff dimension 0 by the work of Einsiedler-Klenback. If this should be easier to prove. But
is there any
in the opposite direction? It can only in formal power series. In formal power series, we can do. But yeah, I don't know. Maybe. That's possible. In formal power series, you can do more things because you can have more information on the inverse. Yeah, I have no information of the Ansel expansion of 1 over psi, or on the base P expansion of 1 over alpha. That's a problem. Okay. Then I will leave this, I will focus on the second aspect of the talk. There's a main aspect of exponent of approximation. So I need to define them. Oh, dp. So nu of psi as irrationality measure, irrational, respectively nu hat of psi is a supremum of nu for which the system acts. Big psi minus a minus mu as a solution for arbitrary large A or sufficiently large So this is simply another way to state the rate of rational approximation of Xi. Measure the quality of rational approximation. So mu of Xi is measure the rate at which Xi can be approximable by rational numbers. So you need that you have infinitely many approximations around this rate, which is less frequent, has not been considered a lot except the last 10, 15 years, is uniform exponent. And it asked that for capital A sufficiently large, you will always find a rational point with 8 at most capital A, and for which big psi minus A is small. So it's so if you want to see this more geometrically, I would say that first you have a family of a convex body, and depending on the parameter Q or capital A, and here you want to find an integral point in, well, only infinitely many of these convex bodies, and here you ask that there should be one in all of them, maybe except finitely many. That's the difference, and of course this is much smaller. So this is classical, and now we can attach. If you consider this problem of approximation, you can define two new exponents of approximations. I will write mu times of Xi and mu at times of Xi. And here I replace the maximum by the geometric mean. So when you see this, the first remark is mu of Xi is at least 2. This is Minkowski's theorem. It's certainly smaller than mu times of Xi. And it's smaller than 2 times mu of Xi, because the product AB is between the max of A and B and the square of the max of A and B. So you have this inequality. And for the hat exponent, we have the same thing. It is not difficult to see that the at exponent of Xi is always equal to 2. In the real case, you can use continued fractions to prove this. In the P-adic case, you cannot use continued fractions, but it's not a big problem. So when you see this, so you have now 4 exponents of approximation. What natural question is to consider their spectra, which is a set of values taken by these exponents. So try to, there is no obvious reason for the spectra not to be the whole interval one can think of. And so try to prove this and investigate some explicit examples. So for instance, I will just put a concrete result. I will take C at least 2, real number, and I will define psi of C is 1 plus P to the power. This is the integer part. So if you consider this P-adic number, you can see very easily good rational approximations. You simply truncate psi C after the G's element, and you have a good approximation. Which is not obvious is that there are no better approximations. It's easy to see when C is large, then you can use some triangle inequalities and you get this easily. But for C close to 2, it's not so clear. And anyway, one can prove that mu of psi mu of psi C is always equal to C. And with best approximations, that there are no better approximations than those obtained by cutting the Ansel expansion. And then you see if you cut the Ansel expansion, you have it's absolutely not balanced because the B here will be, the B will be 1 and A will be large. So that's why when you take the times exponent, you multiply by 2. So you have the difference, large difference between, the largest possible difference between both exponents. And one can compute also, to show that this exponent is non-trivial. The lower bound is, this is probably an equality, but I cannot prove this. So what I said, that it's easy to prove that this is at least equal to C. So the converse is more delicate when C is close to 2. Okay. Keep this here. I'll discuss some result obtained with my sheet on the values taken by this function. So the spectrum of mu times divided by mu is the whole interval 1, 2. So we constructed explicitly or semi-explicitly some numbers which allow us to prove this. So we saw that this is at most 4, and actually this is at most 2 plus the golden ratio. And we don't know if it's best possible or not. What is clear, what I should have written there, is that if you consider this number p to the power factorial g, then this is 3. Take the limit of the result I wrote, you get this. So I got an alternative proof of this. But what we did was we played with triangle inequalities and so on. So it was a bit technical and not so clear. Now I will explain an idea of Kurt Mahler, and yeah. Yeah. You mean, yeah. So there is some work to prove that one cannot do better. Yeah.
No, but what I'm saying is that this example, after you prove it, take a different
Yes. Yeah. But well, it's just truncation. It's just truncating the unsaid expansion. It's approximation by integers.
Do you expect to get a different? One of them I take 3 away.
Yes. It's definitely different.
So this result doesn't fit there. There is a gap between 3 and 3.618.
Yeah.
But 3 is the best.
Yeah.
And you know that it's not the best.
No, I don't know.
I don't know.
I don't know. From the proof, I can see what could be the putative counterexamples, but extreme examples, but cannot say if there are any. I don't know. Maybe we state this first. We'll define some new exponent, and just after explain you why they come naturally in the picture. P is as always. Take a bounded sequence. Then I define rational numbers this sequence of rational numbers we define eta of m by the largest partial quotient of xm is p eta m times. So particular eta of m will be between 0 and 1. M is something divided by p to the m. And after that, eta of c is the lim sup eta m. Eta at of c is the lim inf eta. And we have the following theorem that psi is as this expansion in P-adic, so QP, then in times of psi is 2 divided by 1. Mu at psi is 2 divided by 1 minus eta out of c. So you have a relationship between the exponents of multiplicative rational approximation of psi and this exponent eta associated to rational numbers obtained from the Ansel expansion of psi. Now I will explain why we have this and something which is not, which was probably completely forgotten. And I think it's a very nice idea of Kurt Mahler. Which is in his book from 61. And so as you know, for real numbers, you have the continued fraction expansion with many nice properties. But for P-adic numbers, you don't have continued. Well, there are various algorithms, but with some advantage and disadvantage. And essentially, if you look at this multiplicative point of view, you will see that there is in some way some algorithm. So again, I take psi of this, my P-adic number. I define Cm, so I simply cut here, and I define Xm, Cm divided by P to the m, which is minus 1. Let A be integer such that A be at least 1 and psi minus a P-adic value is less than 2ab. So what I claim is that I can find all solutions to this inequality by looking at the sequence of rational numbers xm, which is a bit surprising, I think. So I take this. So then if I'm m by x I minus AP is p to the power minus m. And you see that 2ab is less than p to the m because of this. We have this. By construction, by definition, psi minus CMP is less than p to the minus m. So we have PCM is also yeah. Yeah. It's capital. This one is capital. It was not enough capitalized. But this one is capital. Just cut. I just cut. So by construction, psi minus CM is at most P minus PTM. Then I replace psi by CM here. So I get this. No. But it will come. Oh. So there is this T integer such that BCM minus A is P to the M T. So the P-adic absolute value of this integer is at most P to the minus M. So it must be divisible by P to the M. Now I divide by P to the M. And then you find that I divide by P to the M. So I have CM divided by P to the M. So I have B xm minus A, which is A to the PM, which is, and this is point, because of this, I get that B xm minus A is less than 1 over 2B, and this gives me that, no, it's minus T, sorry. This gives me that T over B is a convergent to xm. This is an important point. T over B is a convergent to x. So you can, then you basically you find the solutions to this inequality by looking at the convergent to x. But that's the main point. So I will rewrite this a bit differently. So if you want something, if xm has this continued fraction expansion, then there exists G such that T over B is like this. And also one can prove that A is plus or minus the denominator of G plus 2 RK, which gives us that RG plus 1 is essentially PM divided by AB. So you see that the more, if you have a very large partial quotient, then you will have a very good rational approximation for the multiplicative point of view. So it's meaningful to look at the large partial quotient in the continued fraction expansion of XM. So it's meaningful to define these quantities, eta m, and then to take the lim sup of lim f, which is quite standard. So I think this is not known, this kind of thing. So I saw this only in the book of Mahler. So I don't, sorry? Probably, sorry? That's a good question about the primitivity of A and B. So when I define the exponents, mu and mu times, and with hats and so on, I don't assume A and B coprime. So I don't assume A and B coprime. Here, it doesn't matter. Yeah. At T and B, at any case, if yeah. 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 That's a good question. I need to see. I understand. So I cannot answer immediately. That's a good question. Yeah, so, and I may briefly explain, or more or less explain, how one can prove this upper bound by looking at this exponent, but working with this exponent, and actually, so if say you call M is the largest partial quotient of XM, then you have basically you have three cases. So so M minus 1 is Rm divided by P. M plus 1 is Rm over P. I slightly. Okay, you go from from xm. The point is that you go from xm minus 1 to xm by multiplying by p. You have things like this. Plus some integer. So if you look at the continued fraction expansion, if you multiply by p, then the partial quotients will, if there is a large partial quotient, it will be either divided by p or multiplied by p. Then you have to round, but that's basically the thing. So it's oscillate. So if you, this can be written precisely. So then you have this kind of evolution. So eta m and eta m plus 1 cannot differ too much. So you play with this. And then you can get this result. Actually, you prove that it at is less than 1 over root 5 for every c. Can prove this, and this implies the result. And the case there is the extremal case for which I cannot say anything. If you have your, I would write, say your xm, so something divided by pm, and if there is a partial quotient which has whose size is pm over gamma, and the second partial quotient whose size is pm over gamma square, where gamma is the golden ratio. Okay. And if you have this situation which repeats, I cannot prove that this exists. I cannot prove that it doesn't exist. If you have this situation with, so xm, you have this large partial quotient which is extremal in some sense. So you have this after for the next xm plus 1, etc. This partial quotient becomes like this. Here it increases. So here you see your level of eta hat. And you have another one which comes from here. You have something like this. This is more or less the picture. And well, I tried many ways to construct explicitly. The problem is that it's difficult to know something on partial quotients of rationals, and especially of rationals with denominator a power of p, or a power. So it's not, it's very specific rational. I cannot force to, if I force large partial quotients, then I don't end up with a rational with the denominator a power of p. So that's what I don't know. But well, I think there may be new ideas to find, and it's absolutely not hopeless to make some progress, and perhaps to prove that 3 is best possible.